In the notes for Unit 5, Lesson 8, we will cover percent yield. Percent yield, or for percent yield, you will be able to compare the theoretical yield to the actual yield to determine what percentage of product was produced. So here are some terms that are important. Percent yield is the ratio of actual yield compared to theoretical yield. So if you wanted to also add this equation to your notes, the percent yield, to find percent yield, you would take your actual yield divided by your theoretical yield. And then you would take that times 100 to change it to a percent. So you take your actual yield divided by your theoretical yield. Actual yield is the amount of product that's actually produced in an experiment. So if you are baking cookies and you actually made 21 cookies, that would be your actual yield. The theoretical yield is the amount of product that should have been produced. So this theoretical yield is a calculated value based on your ingredients. So if you are baking cookies and the recipe says this recipe will make 24 cookies, that would be your theoretical yield. So theoretical is if everything goes perfect, how much should be produced. So it's the amount that's expected. All right, so this is the example that's in your notes. This has several steps to it because first we have to find the limiting reactant when we're given both amounts of reactant, and then we have to find our theoretical yield. So we have to figure out how much should be produced, and then we have to compare how much actually was produced to find our percent yield. So like I said, this has several steps to it. So finding the limiting reactant is a review from what we did a day or so ago. So you are given the amounts of C2H2 and the amounts of O2. So remember, when you're finding your limiting reactant, you are comparing the two reactants. One thing that's different about this reaction or this equation is that the values that are given in the problem are in moles. Usually they've been given in grams, and then we find or we take grams and convert it to moles, and then we compare using our mole ratio, and then we would go back to grams. Well, in this case, we're already starting with moles, so really this is the only step that we need to do for this particular reaction, only because the numbers given in the problem are in moles, so we don't have to do that extra conversion. So again, when you are finding limiting reactant, you're going to compare the two reactants. It does not matter which value you start with, but you are going to compare C2H2 to O2. So if I start with the first number given in the problem, I would be starting with C2H2, which in that case, I would be figuring out how many moles of O2 are needed in this reaction. So, oops, sorry, I labeled that wrong. I apologize. This should be moles. So remember, whatever unit you start with on the top gets transferred to the bottom of the next step. So here we're in moles, and we want to know moles of O2. So this step is going to be your mole ratio, which comes from the balanced equation. So we're comparing C2H2 to O2. So we know that there are 2 moles of C2H2 for every 5 moles of O2. Moles of C2H2 cancels out. This gets us to moles of O2, which is what we want. So then we can just multiply across and divide. So 2.4 times 5 divided by 2 would give me exactly 6.00 moles of O2. So remember, when you are figuring out when you're figuring out limiting reactant, the amount of the other reactant that you need, or when you calculate your value, that tells you how much of the other reactant you need. Now you have to do this comparison. So we have to compare how much we need to how much we have. So we need 6 moles of O2. From the problem, we have 7.4. So this is how much we have available. So we need 6 moles. We have 7.4 moles available. So we have enough O2. So since we have extra O2, that is going to be our excess reactant, which then by default, if O2 is our excess reactant, then C2H2 is going to be our limiting reactant. Whoops. So C2H2 is going to be our limiting reactant because from our calculation, we know that we have extra O2. So then by default, the other reactant would be our limiting reactant. So then when we're finding theoretical yield, we have to start with our limiting reactant. So since C2H2 is going to limit the amount of product that we get, then we always have to start with that substance. So now we're going to compare C2H2, but we want to know how much we're going to produce. Our two products are CO2 and H2O. So if you look at step 3, finding the percent yield, it says, what's the percent yield if 39.8 grams of water? So because we want to know how much water is produced, that's the product that we are going to end up with. So CO2 is produced in the reaction, but for this specific example, it doesn't matter to us because we want to know how much water should be produced so we can compare it to how much was actually produced. All right, so we want to know how many grams of water will be produced when this C2H2 is going to run out first. So we have to start with the C2H2 that's given in the problem. Now, again, remember, we're already in moles. So whatever unit you start with goes on the bottom of the next step. So now we're already in moles, so now we can compare moles of one thing to moles of another. And from our balanced equation, we are comparing our limiting reactant to water, which is one of our products. So for every 2 moles of C2H2, we are going to produce 2 moles of water. So again, that comes from your balanced equation. Moles of C2H2 cancels out. We want to end up with grams of water, so now we have to go from moles to grams. Whatever unit you have on top gets transferred to the next step. So when we're going from grams to moles, we know the molar mass is the amount of grams in 1 mole. So in 1 mole of water, we are going to look on the periodic table to add up the mass of 2 hydrogens and 1 oxygen. So oxygen is 16.00, whoops, I wrote this down wrong, 16.00 grams, and hydrogen is 1.01, and you have 2 hydrogens, so you have to take it times 2. So that gives us a molar mass of 18.02 grams of water. So now we can multiply the numbers across the top and divide by the numbers along the bottom. So when we do that, we end up with 43.2 grams of water. So this, remember, is our theoretical yield. So what that means is if everything goes perfect in this reaction, we should produce 43.2 grams of water. That's how much should be produced if everything goes perfect. Well then, problem number 3 says, what's the percent yield if 39.8 grams of water are actually produced? So we know how much is actually produced, and we're going to compare it to how much should have been produced. So for your, percent yield, thanks. Again, you take your actual yield divided by your theoretical yield, and then you have to take it times 100 to change it to a percent. So again, our actual yield is what was actually produced in the reaction, and we're comparing that to our theoretical yield, which is what should have been produced. So we should have gotten 43.2 grams of water, but we only got 39.8 grams of water. And then of course you have to change it to a percent. So when you multiply and divide those, you end up with 92.1% yield. So you were able to end up with 92% of your product produced after this reaction, which is a really good percent yield. So again, make sure that you understand the difference between all the terms. So you have percent yield, theoretical yield, actual yield. So there's a lot of different terms to keep it straight. But then also make sure you look back in your notes for the process to find the limiting reactant and the theoretical yield first in order to then calculate your percent yield. So again, let me know what questions you have. You guys are doing a great job.